TJ Maxx. Mr. Donahue, that's his favorite.
24 hours in a TJ Maxx and not get bored.
Well, you have to look that long because there could be like things that are like hiding and stuff.
They are. They're always hidden. There's always new things there. That's why my parents don't take me to TJ Maxx because they can't ever get me out of this shit.
And I don't like going there with Mr. Donahue because he shops for so long at TJ Maxx.
He likes to shop.
He loves to shop. I would say he's probably over half my clothes he has picked out and bought.
I'm gonna imagine like you're gonna buy it.
Well, like my most favorite like dresses I've worn to a wedding, he like ordered on the internet for me. Like it was like, you look cute in that, and then like it came and it was adorable. Like it's so cute. Like so.
Wait, hold on. I find that very odd because of the fact that he dresses like he doesn't know how to.
I know.
Yeah.
He's horrible about himself, but he's great for me. Like I don't know. Like I know you think the guy has like no sense of style, but like he does a pretty good job.
Me personally, being someone who like is very picky about what I wear, I usually don't like when people shop for me, unless it's for like pants because people know what I like when it comes to pants, and that's pants with pockets.
Pockets. That's
all I need is pockets.
Yeah, Justine, my parents, every time they try to pick something out for me, it's like, hey, you. Disgusting.
Yeah, my mom has. My mom's gotten a little bit closer to understanding my style.
It's like,
Yeah, literally, you've seen my style out of school. It's like, how small is your pocket?
it's not that small.
I don't even know how to describe it, but the stuff that I wear outside of school is very different. My parents have gotten a lot better. My stepmom, she went to Target. You know Wild Fable, that brand that they have in the front of the store? And she found like the cutest stuff in there. She knows that's my outfit section.
Surprisingly, at Christmas, like picked out the best gift I've ever
Oh.
gotten. One of the best gifts I've ever gotten. Him and Dad went to TJ Maxx or whatever, and they found a friend's Christmas sweater, and I literally had a stroke. When I opened it, I was like, I think I've given like the best gift he's ever gotten. And, well, probably wrong, but I've gotten second because I got him a loop right.
One of my favorite things was the Jack Skellington pajamas, the full body one.
Oh, I actually have that pair.
Okay, guys. So, all right. So we'll talk about factoring these two types. Now, just a reminder, guys. These two are two different types of factoring. They're very, very similar to each other, but the one is I can think much easier than the other one. So notice when there's something in front of the x squared, we can automatically go to this type of factoring where I don't have to do the x thing. But over here, if there's no GCF, we do have to do that x. So kind of trying to remember the difference between those two. Now the x thing does work for the one on the left, but it's probably easier to not have to worry about doing that. So just that quick reminder as you guys are working here. Hi. Right. Yeah. Okay. Yeah. And you get stuck, that's okay. We'll talk about them here in a minute. stumped here, just remind you guys how to do these types of problems. So on one like this, we don't have to worry about multiplying that first and last term. We can just look at this last term, and we want to multiply to get this number, but we want to add to get this one. So multiply to positive 16, add to negative 8. So in order to multiply to a positive but add to a negative, they both have to be negative. Oops. And then in order to get that negative 8, it's going to be minus 4, minus 4. Now technically, this is what we're going to be talking about today. These are called special cases. So when we get the same thing twice, I'm fine with you leaving it this way. Your book, though, if you were like checking your answers in the back of the book, it would write it this way. It's just the same thing twice. So either one is fine with me, so one or the other is fine. But when you get the same value twice, it's considered like a special case there. Now this next one, like I said, this one is one that we have to use method we learned yesterday, where we multiply this first and last term together. And we put that on the top. So I do 4x squared times 9. So that's 36x squared. Then on the bottom, I'm going to put the middle term, so 12x. Oh yeah, sorry, I don't need to find.
I know where they are.
Unless I knew them.
You're gonna change it up on me.
All right, so we're going to multiply to get 36, but add to get 12. So we're multiplying to get this one, adding to get this one. So this time it's all positive, so I don't have to worry about negatives. So 1 and 36, and some of you guys already got it, but oops, too many lumps in my 36. 2 times 18, 3 times 12, lots of factors, 4 times 9, 6 times 6. No. I thought it was behaving for a little while and then 7 times 6 times 6. So in order to get that 12, it's going to be 6 times 6. So 6x and 6x. Now this factoring is not exactly the same where I can just automatically put those in the parentheses. If you guys recall, that's what we do to split these middle term up. So we're going to break up that middle term to make it 6x and 6x. So technically, we should have been able to do this yesterday, but this is considered a special case because of the types of numbers we end up with. You don't need to know it's a special case, but what can come out of 4 and 6, 4x squared and 6x? And 2x, right? And out of the 6x and the 9, we can also take out a 3. So we'll be left with 2x plus 3. A lot of 2x plus 3's going on here. So we have the same thing twice, so we're going to write that out in front. And once we do that, we take that out of there, and what we're actually left with is also 2x plus 3. So we actually get the same thing twice again, just like we did on the other side. So again, these are considered special cases when we get the same thing in both spots. So you can leave it this way. Like I said, if you like checking things in your book or something, they'll write it like this instead. They'll put it like kind of try to be a little more efficient. But I don't care. Either way is fine with me. Just that you're comfortable with the fact that it could be the same thing. Right, questions there? All right, so we're talking about these are called more, we're talking about more special cases. Now a couple of these two we've actually already talked about before, is these difference of squares. This is called the difference of two squares. It comes up pretty often in here, but then my geometry students from time to time will see problems like this, algebra 2, showing up in our problems. So if you guys recall, the way I suggested you guys think about these ones is, what's the negative 9 stand for in terms of my terms here? What is the negative? So is that our A, B, or C? The negative 9. Is that A, B, or C? That's our C. Because if this is our equation, the C never has a variable on it. So this would be our C value. So I know it's going to be x times x. I want to multiply to get negative 9, but I'm going to add to get what in this case? There is nothing there, so I'm multiplying to negative 9, but I'm going to add to get 0. So again, this is a special case that I want to multiply to get negative 9, add to get 0. That means they're going to be exactly the same number, but just the opposite sign. So minus 3 plus 3. So when you see ones like this, I'm hoping you're going to start to notice there's a pattern there. Same thing goes for this one. We want to multiply to negative 64, but add to get 0. So again, it's going to be M and M. Now you want M&Ms. M and M. And we want to multiply to negative 64, but add to get 0. Now, being a little bit smart about this, well, this one, they were the same number, but the opposite sign. Is there a number that multiplies by itself to get 64? Not by itself. What times what? What times itself equals 64? 8. If we use negative 8 and positive 8, will that give us 0? Yep. We multiply to get negative 64, but add to get 0. So this is called the difference of squares. So kind of the way to be aware of this is the difference of two squares. So it has two terms. That's your first clue that you're going to be using the difference of squares. The second clue is in the name. They're squares. That means they're perfect squares, so they're square roots. And then the last thing here is the word difference. What does difference mean in math? What does difference mean in math? Subtraction. So I'm subtracting 2, obviously. Squares, they're considered perfect squares so that you can take the square root of. So difference of squares is that we're subtracting 2 perfect squares. So if you look at our problems, examples 1 and 2, I have x squared and I have 9. 9 is considered a perfect square. I could take the square root of 9. Square root of 9 is 3. M squared is a perfect square. It's something being squared. It's 64. I can take the square root of 64. It's 8. So these are both perfect squares and subtraction. Now, letters A and B are showing us ones that don't work. So these two don't work. Why is letter A not going to work? Yep.
Because 2 negatives multiplied times a positive, but 2 negatives subtracted from each other.
Yeah, so like basically she's saying there's no way to get the 9, multiply to get the 9 and get them to cancel. It's because this is essentially just addition. This rule is only for subtraction. So since this is addition, I can't use this rule. So on a problem like this, I'm not able to use the rule. Now letter B is subtraction. So that one should work, right? What's wrong with that one? Why does that one not work? Yep. The exponent's too big, it's not like a 2. Actually, like a 4 would work as well. But how about the 8? Is 8 a perfect square? No, no number times itself is going to equal 8. So the fact that this is a third power and this is not a perfect square, we can't use that one. So there's only certain problems that work nicely for this. It has to be 2. It has to be perfect squares, and it has to be subtraction. So the rule for this, though, if I have my perfect squares there, and I'm subtracting them, I'm going to write the rule in the parenthesis there. So if you guys look up here, if it's x squared, I know it has to be x times x. So if it's a squared, I know it has to be a times a. Now b squared, we don't typically have one that has 2 variables like that, but if b squared, it's going to be b times b. What do you guys notice about the signs in this one, in both of these? In order to get that middle term to cancel, what has to happen to those signs? It's a plus and minus, plus and minus. So in my parentheses, this can be a plus and minus, or minus and plus. The order you put them in doesn't matter. So when we see problems like this, I don't necessarily have to spend a lot of time going, what multiplies to give me negative 64 but adds to give me 0? Once you get good at seeing these, you're going to be like, oh, that's obviously a perfect square. I can just use that other number, or use the perfect square number. So I'll show you guys an example of these. Now, these ones are a little bit trickier. Because these ones initially look harder because there's a number in front of the 16, or in front of the g squared. But is 16 a perfect square? Do you guys know how to check that? Do you know the square root button in your calculator? There's a square root button in your calculator. If you take the square root of 16, it will tell you that it's 4. If you're ever unsure about 16, or like any number, the square root of 16 is 4. That's how we know it's a perfect square. So 16g squared, so it has that squared. How about 1? Is 1 a perfect square? Kind of a weird question.
Yes.
Yeah, 1 times 1 is 1. So those are both perfect squares. So, and it's subtraction. So we're going to be able to use this rule. So you don't have to do all the multiply to get this, add to get that in these problems. You can kind of just skip that. So 16g squared. What times what gives me 16? 4. So I'm going to use 4 and 4. What times what gives me g squared? How am I going to separate those out? G and G.
What button shows you what square root is?
There's a little, looks like a little check mark square root button. Should be underneath. Yes, but you have to do, so it's clear first. So do that button first. So second is that, and then hit 16. There you go. And okay, so if you tried square root of 8, like I said, that's not a perfect square. You have to do the other way around. So that's telling you it's not a perfect square. So you guys, on your calculator real quick, I was just showing Isaac this. So I told him to check like the square root of 8 in his calculator. Some of your calculators will give you a decimal. Others of your calculator will write it like this. That's the way you know it's not a perfect square. So if it leaves a square root in the answer, or if it gives you a decimal, so it depends what your calculator does with it, that means it's not a perfect square. But if you take the square root of 16 and you get a whole number, that means it is a perfect square. Okay? All right, so we got 4g times 4g gives me 16g squared. We said 1 times 1 will give us 1. And what do I have to do with the signs? Just positive and negative. That's all we do. Now, if you're doubting this, you're like, really? That's all we do? It's just these are special types of problems. They're unique. Just like when anytime you say something special, you're saying that it's like different than the normal. These are easier problems because they're set up this way. Now, if you're like, I don't trust you, that doesn't work, you could always FOIL. Read my shirt, FOIL. So you could FOIL there if you're unsure. So the order of the variables, it doesn't matter, so don't let this bug you. So let's look at this next one. This might be one you don't even know for sure. 121, is that a perfect square? It doesn't really sound like it would be, because like, I don't know, maybe it's like kind of an oddball number.
11.
It's 11, yeah. Square root of 121 is a perfect square. Is 4a squared a perfect square? Yeah, 4 is 2 times 2. Hopefully that's one you just know. So we're separating the 121 out as 11 times 11. So this one we can do pretty easily because there's a rule for it. So 4a to the second, how do I break that one up? What two things do I break that up as? A, but also what number do I need in front of it? 2. So 2a and 2a. Now I know there's other things that multiply to give me 4. 4 times 1 also gives me 4. But if we're doing the difference of squares, then we're going to use those perfect square like roots to figure out our answer. And then again, just put plus and minus in there. Do these last couple and then we'll take a break. So, m squared, how does that break up? M and m. Always talk about m and m's. How about 25? Is that a perfect square?
5.
Yeah, 5 and 5. And n squared is good, right? So we're going to break this up as 5n and 5n. And then we do a plus and minus. All right, if you guys want to take a minute to look at the next one, I'm going to tell you guys I don't truly love the next one. I'll show you guys something about it that makes it a little bit tougher. Why don't you try that next one, see if you guys can figure it out. I'm going to talk to you about why it's a little bit of a weird one. All right, yeah, you probably are like, ew, am I doing this right? It's possible there's an extra little piece to this one that I kind of like forgot to mention, like kind of one of those things that makes it a little bit funky. Most of you guys probably did the straightforward way, and that's great. Let's do it that way first. So, I'll show you guys what else you can do with this one though. So 36 is a perfect square. What did you guys find out it is? 6. Maybe you just knew that too. And then the j is going to be 6j times 6j. And kind of the way to check this is, does that work? 6j times 6j, yep, 36j to the second. Then the 9 is also a perfect square. What times what gives me 9? 3. So 3k and 3k. And then we do our plus and minus. Technically, I'd be okay with this answer. However, there is something about it that makes this one technically not completely factored. Does anyone see it? This is not like if I want to be really, really picky, this is not technically factored. Yep, completely. It can be simplified, kind of. You can still pull something out of this. Do you guys see it? They all have something in common. Yeah, 3. So technically, we really should divide 3's out of this and put them on the outside. However, this is a really weird one. What we could have done to begin with, to make this a little bit easier, is to begin with, we could have actually taken a 9 out to start. And if you didn't see that, it's totally okay, because I kind of forgot to mention that GCF thing. The GCF can still apply here. So I actually could have taken a 9 out to begin with. And it's totally okay you missed that. I didn't notice it until I was just about to say do this problem, and I was like, oh man, this one's supposed to be a little bit tougher. So do look for that GCF, because technically this is going to be a little bit better answer because it's going to be fully factored. Because this is still a perfect square. It's 2j and 2j. And then that k squared is just k times k. So it makes it a lot easier to take that number out to begin with. So technically, if we wanted to be really picky, you'd probably get a point off on that if I said to factor that completely. If you wanted to still factor it, you could take a 3 out of this one. But then you have to take it out over here as well. And then we'd put them together. So 3 times 3 is 9. That's where the 9 comes from. It's a lot easier to do it right away if you can remember. But that's kind of a little extra tough problem there. Okay? So let me stop this and get us online here.